All right, this unit is on momentum, and we can certainly look at momentum as object A hits object B and what happens, but things can have momentum even before they hit something. So I very often think of momentum when I'm at Costco. I usually start with an empty cart. I'm not really in a hurry, and so I don't have a lot of momentum I'm running around with. Pretty soon I've loaded up my cart with some brimstone and a little Diet Coke, and I'm in quite a hurry to get out of there. And that's usually about the time the person in front of me decides to stop because they just have to taste a Ruffles potato chip because they've never tasted one before. So, my cart. When I begin, low mass, low velocity. That would equal low momentum. Easy to stop. After a little shopping, it's loaded up, it's got a large mass, my velocity has increased, my momentum has increased. Much harder to stop it at this point. So let's look at some examples of other things. We all know that I like it when people fail epically at physics. And when I was in college, there was somebody protesting a train. And I remember it so well because they sat on the train tracks in front of the train to protest it. And yes, the conductor hit the brakes. That really didn't help the person very much because a train, kind of like the tanker here, has a large momentum. It can't just stop on a dime. It just doesn't. And yes, the person lost their legs, but everyone will be happy to know they survived. But that's an epic fail in physics because you can't sit in front of a train and think it's going to stop. Sorry, you just can't. Too large of a mass, not going to happen. Another example of something that has a large momentum are bullets. Not a huge mass, but they're going very, very quickly. So again, they have a large momentum. All right, so let's look at how momentum and force relate because we've just finished force, so now we're going to combine these. And as we look at movement of objects, you can look at force and you can look at momentum, and then in the next unit we'll look at energy, and when you have all three of those things, then you can pretty much describe all movement. Right now we're just going to start by combining momentum and force. So remember when I said that you can't just stop something with a large momentum? Yeah, that would require a large force to stop it. That's why when you're running around Costco and your cart's really, really full and the person stops in front of you, it's very hard to either swerve and miss them or to stop. I'm not saying I've ever hit anyone. I'm not saying that. I'm just saying it's hard not to. Okay. You can also apply a small force over a long time if you need to stop something with a large momentum. All right, so you can do one or the other. And so when you think about catching something and not breaking it as it approaches you, the more give you have in your catch. If you're catching an egg or a very full water balloon as someone throws it to you, if you can kind of extend your arm back and stop it slowly, you apply a small force, but you've extended the time it takes. You can also stop something with a large momentum. So it's going to depend on the momentum, the force, and the time interval, the time that the force is applied. All right, so again, this is momentum and its relationship to force. We have our basic equation. Momentum gets P, sorry, M is taken, but it's a P for momentum. So P equals mv, that's just, mass times velocity. And as we look at the rate of change of momentum, it's equal to the net force. So if you can look down here at this formula here, the net force is equal to the rate of change of momentum over time. So how quickly we have to change our momentum and how long we do to take that. We can look at how this you've seen this formula before in the form of F equals ma, right? Mass times acceleration. Remember, acceleration is just velocity over time, so we just plug in velocity over here, and you get force equals mass velocity over time, which force equals mass velocity over time. Mass times velocity is just momentum. So that's how you end up with this equation. It's actually nothing you haven't seen before. We're just introducing the concept of momentum here. So how quickly we change our momentum and how long it takes us is going to tell us the force we need to apply. That's Newton's second law. We've done all that. We're just kind of reworking it here. All right, so let's look at collision and impulse. When we study momentum, we also like to introduce collisions, and we're going to introduce different kinds of collisions. But one thing we have to look at is something called impulse. An impulse is the amount of time we're going to apply that force. So we're going to have a force, and how long are we going to apply that force? It is actually the same equation you just saw, and we rewrite it multiplying it by time. So the one you saw on the previous page, we have the force equals the change of momentum over time. We multiply each side by time, all right? So we want to see how long we're going to apply this force. So we introduce the concept of time, and then force, change of time, equals your change in momentum. And that is the definition of what impulse is. The impulse is how long we've applied the force, and for how long we've applied the force. How big the force is, and how long we apply it. Large force, small time, isn't a huge impulse. Large force for a long time is going to be a greater impulse. Okay, one way to think of how we do this is objects have momentum. When I'm running around Costco with a fully loaded cart, it has its own momentum. The impulse is the force we're going to apply to act on this object. Okay, so as we look at collisions and impulse, let's look at slowing things down again. Remember when I talked about catching the balloon? If you could, if you catch the balloon and you don't move your hands and you just hold it like a rock, that balloon explodes. All right, but if you give it a little bit, if you kind of give in a little bit, you can catch it without exploding it. You can reduce the force on it by increasing the time. Same thing if you jump. If you jump and you land and you don't bend your knees, that time is very, very quick, right? If the impulse time, the change in momentum, is very rapid. If you bend your knees and slow down the impact, then the force acting on you is less. The force on your knees is less. Everything's better in life. You didn't need to write that down. That was all in gray. Okay, same idea here. And if you throw a raw egg, actually, I'm sorry, this should be in gray too. You don't need to write this down either. Throw a raw egg as fast as possible at a plastic sheet that's held loosely. Hopefully it won't break, right? But if you hold it tight, then you can break the egg. So, okay, same idea here as the previous one. This is a check yourself. You have an egg over here. It has a, medium mass, but you threw it hard, velocity. Now here's the catching time. If we let this kind of absorb in and catch it for a while, we've increased the time, all right? So that we've increased the time, longer time, smaller force. If it hits a wall or a brick or anything really hard, the time is short, right? The time it takes to stop it short, but the force applied to it becomes much, much larger and your egg breaks. Okay. This is applied to automobiles. I don't know why it took them forever for them to apply this to football, but they have applied this to automobiles forever. If you look at an automobile, the whole idea is to slow you down slowly. So look at the right-hand picture over here. They have something called a crumple zone. They actually design cars so that this area crumples up. The idea is that if this were really strong and rigid and you hit something, then you stop very, very quickly and it injures you here. But if you can use this crumple zone so to kind of soften that crash, and they actually design it to crumple without having the engine shoved into you, is the idea of the crumple zones. If you can slow it down, then you can increase your safety. And football helmets, they actually did the opposite. They used to have these things called leather heads. It was just a piece of leather. They actually were fairly good for your low concussion, low impact stuff. Not great on the really heavy duty stuff. And they went to that hard outer shell. Well, the problem with the hard outer shell is that you stop something very, very quickly. And again, if you stop something very, very quickly, you've increased the force. I think just in the last couple of years, they've actually added crumple zones to football helmets. They have little parts that now indent. Same idea as a crumple zone. All right, so let's look at collisions. When two objects collide, the impulse is equal and opposite. Remember kind of equal and opposite here? Equal and opposite. If you have two things rolling at each other, they should bounce right off each other with an equal and opposite impulse. All right, conservation of momentum. So after a collision, the momentum has to be the same as before the collision. So again, you have to define your system here. You can't take the whole world, but if you have two objects, the momentum of A and B together, so if you have over here, you have A and B together, has to equal the momentum after they hit. So if A and B are moving towards each other and they hit, their total momentum has to equal after they have hit. It has to remain the same. So if they're coming with a momentum of, I don't know, 10 Newton seconds this way and 5 Newton seconds this way, you would have a total of negative 5 Newton seconds. It has to be the same over here after they have hit each other. You can't suddenly add momentum. All right, so this is how we write out the conservation of momentum. If you want to write the formula out, is that if you have the mass of object A and the velocity of object A, and the mass of object B and the velocity of object B, yes, you're writing this down, this part, that equals the mass of object A and the velocity of object A, and the little prime here, that prime means after the collision. Yes, you could write after here, but you're just taking more time. So prime is after collision, plus mass of object B and velocity of object B after collision. All right, just saying again, the conservation of momentum, that's the formula. So when I ask you to find it, you just add the original momentums of your objects, and that better equal the final momentum of your objects. All right, law of conservation of momentum, and this time, just for fun, we have some numbers to play with. If these two objects are the same mass, make our life easier because we're doing a slideshow here. If they're the same mass, this and this have the same mass. I don't need to know what that mass is because those masses will all cancel out if I put them into that equation. So it could be anything. If you want to put in 100 for your equation, knock yourself out, but you actually don't need it because they're going to cancel at the end. If this were at rest, this is sitting, and this comes along and hits it, and it's going 24 meters per second, and the two of them move off together. If the two of them move off together, what would the velocity be of this one? All right, do another one. If this one's moving 24 meters per second, this one's at rest, and then after the collision, A stops. This one's 0, it's now at rest, and it transfers all of its momentum to B. What is the velocity of B? All right, did you guys get that? So for the first one, I'm hoping that you would have gotten half, 12 meters per second. That if A hits B and they both go off together, then they should both go off together with half the velocity because there's twice as much mass there. But if A hits B and they don't hook, they don't link up, and A stops and just B goes off by itself, then B would go off at the same velocity that A hit it with, 24 meters per second, because they have the exact same mass. All right, you don't need to write that down. This is, just for fun at this point. But conservation of momentum works in outer space as well. Of course it does. So one thing you can do with rocket fuel is just expand the gas. And because you're expanding the gas, you're shooting it out one end. And, with any luck, you're shooting this out with a decent amount of velocity because you're not going to get a huge mass here, but you need a decent amount of velocity. It will propel your rocket in the opposite direction. All right, so if you have what's called an elastic collision, you get an equal exchange of momentum. And most of the collisions we're going to be looking at are going to be called elastic collisions, means the momentum is transferred. A nice example of what we would call an inelastic collision are balls of clay. they hit each other, they stick together, they deform. You don't get a perfect transfer of energy there. They actually spend some energy in deforming. Also, an inelastic collision would be when those two boxcars we had earlier, if they couple and stick together, if there's any sticking together, that's an inelastic collision. An elastic collision, they bounce off perfectly and you get just a nice equal, MV equals MV after collision. Okay? Newton's balls are designed to be elastic, good examples of elastic collision, right? They make it with nice steel balls. They transfer the energy well. They would never work if those were little blobs of clay. It would never happen. I know you guys know how it works. You take one off the end and you release it, and one pops off the other side because the mass and velocity of the one on the right has to equal the mass and velocity of the one that ends it. And then if you take two off on the right and release it, it transfers through the balls and you will get two kicked off on the left side, again, because the mass and velocity that you have put into that system has to come out on the other end. Okay, so when can we use our science in real life? And clearly the best real life example is playing pool. So when you play pool and you have the 8-ball right on the edge and it's right on the edge of your pocket, you want an elastic collision. You don't want these to stick together. You have to make that collision very crisp and very distinct. So you don't actually send a slow ball towards the pocket. It is actually better to give it some energy and some speed and it'll bounce off. You'll have an elastic collision. And that is a property of collisions, that bouncing off, that elasticity. A slow ball, they can both go the same direction after the collision because your total momentum's the same. It will be in the direction of the pocket. So if you're going to bounce your cue ball backwards, you have to actually have that 8-ball go faster towards the pocket and then your original cue ball, right? It's got to bounce faster because it's going to have to take up some of the momentum of the backwards moving cue ball. The only way to get that elastic collision is for a crisp, quick collision. You got to have some speed behind it. You can't be a wuss. All right, inelastic collisions. Again, if things couple together or stick together or crumple together, those are all examples of inelastic collisions, all right? Any like clay sticking together, anything that sticks together, anything that deforms significantly, we will not get good measurement of an elastic collision on. Okay, here's just for fun, you guys can do the math. If you have a 4-kilogram fish swimming 3 meters per second towards a small 2-kilogram fish and swallow it for lunch, what is the total momentum before lunch? Well, we only have the mass and velocity of the large fish. So we're going to assume the small fish was just hanging out. That means 0 momentum. So you have the large fish at 12 Newton seconds going to the right and the small fish at 0. So the combined after lunch must be 12 Newton seconds to the right. So you would have you would end up at 2 meters per second to the right. All right. Momentum also kind of explains the recoil. We have, you have a gun, a cannon, or anything, and you send that cannonball out with quite a large velocity. In this case, it's going to the right. Well, you have to have equal and opposite momentum going backwards. You just do. This is the kickback. This is whatever. This is your recoil. And so to reduce that, cannons can be made very, very heavy. You can do different things to try to reduce recoil, but the reason it is there is because of conservation of momentum. Okay. We're going to look at complicated collisions, and what I mean is, there's some vector analysis coming your way. Okay. So if you have collisions that go in 2 dimensions, we're definitely not doing 3-dimension collisions. I'm not crazy, but we will do a couple 2-dimension collisions. And really, if you just kind of calm down and relax, it's not that hard. If you look at this problem, you would have A coming in. You have ball A here coming in. And so if you make this your x-axis and you make this your y-axis, first thing you got to do is just define your system. We know it has a momentum in this direction, right? The momentum has to be the same in this direction. What we do though is we say, look, the momentum here is some number given to you. You have to have mass and velocity. But the momentum in this direction is 0. It's not moving in this direction at all. So it's 0. That means that A and B, their momentum better equal 0 in this direction, right? So as we take, and for this you're going to do opposite over hypotenuse. So you're going to take the sine of theta to get the y direction here. When you take this one and you take this one, sine of theta again, these will equal out. They'll equal 0, right? Or we will force them to equal 0. And then in this direction, in the x direction, this mass and this mass's velocity, both of them mass times velocity, will just have to equal whatever the initial condition was over here. The initial momentum, we will practice this in the daily question, relax. But this is the basic idea, is that we will have something going in this direction, and we will have, we'll break it down into x and y components, and you'll just look at what's the momentum in the x direction, okay? Solve that separate and distinct, and then do what's the momentum in the y direction, and solve that separately and distinctly.